All right. Hey everyone. We are live from, I guess we're about a mile underneath the Earth's surface here in the Sanford Underground Research Lab in South Dakota. And when you think of South Dakota, most people probably don't think about really high-tech research labs, which is why I thought it would be interesting to go live from here. This completes a series that we've done where last year we went live to the International Space Station. So I thought that was pretty neat at the time. So now being able to go live from a mile underneath the Earth's surface kind of gets the other end of the spectrum and showing that we have connectivity down here and the ability to broadcast live to all these people around the world. So the work that's going on here is interesting on a couple of fronts, both the science and the community. And I'm going to ask a couple of folks who work here to come over in a second and talk about some of what they've experienced and some of the work that they're doing. Scientifically, being a mile under the Earth makes it easier to pick up signals around things like neutrinos with some mask from the rock face above this, so that way you're not picking up all the cosmic rays from the sun. So it makes it so that you can build equipment that can kind of detect the different particles and the different states of things without distraction from the other cosmic rays. So they'll get into that in a little bit more in a second, and what the implications of that are for understanding the universe and a lot of the different cutting edge of physics. The other thing that's just super interesting about this place is it used to be a gold mine, right? So if you go back, I mean, how recently was this active? I mean, 15, 17 years ago? Yeah. Right, I mean, this was the largest gold mine in North America, I think maybe even in the whole Western Hemisphere. And I think that this place produced about, what was it, like 3 million pounds of gold or something on that order of magnitude. So, one of the interesting things that, as we go around the country for this year of travel, that we've seen as a theme is, there are a lot of places that have had their economy primarily focus on natural resources or on the land that are shifting to modern knowledge economies and making it so that rather than people fighting over resources, if one person has gold, that means another person doesn't have it. With a knowledge economy, that's not the case. You learn something new, you discover something, and everyone can benefit from that. So as a lot of these facilities in the economy gets upgraded to a modern knowledge economy, that becomes positive sum, and really everyone can benefit from that. So before going on for too long on this, I want to introduce a couple of the folks here on the science side to start. This is Jared. He's the scientific director here in Cabanan, who was running and just explaining to me one of the interesting experiments that you guys are running on detecting neutrinos and trying to understand basically what is going on with matter and antimatter in the world. Right. So I don't know if you want to start off just talking about why this experiment is important for the world and what exactly you're testing for and why it's good to do here.
So this is the Myrana demonstrator experiment, which is under nuclear physics. And we're trying to understand the behavior of a neutrino. And it's kind of interesting that we're shielding ourselves from everything around us so that we can try to not see a neutrino and look at this rare occurrence that's called neutrinoless double beta decay. And hopefully this will give us more of an understanding on why there's matter in the universe and why we're here. So scientists come from all over the United States and all over the world that are part of this collaboration. Students, scientists from universities, Department of Energy, they all come, and we've been assembling this experiment for 5 years. We've finished, we're taking data, and it opens up so many possibilities in this area.
So talk a little bit about how the experiment that you're running with Fermilab. So basically you have this other lab that's, what, 500 miles away, right, in Illinois, that is sending neutrinos out over here, and you're basically trying to tell whether the state changes to be, 1 in a billion of neutrinos or so converts to being, I might get this wrong, but not antimatter neutrinos, but antineutrinos,
different flavors.
So trying to explain why, what we observe in the world is more matter than antimatter when you look out there. So talk a little bit about that experiment.
Well, so long baseline, so this would be the far side detector, and you're looking at the beam of electrons coming through and understanding how it is that they leave from Fermilab, and then what is the change that occurs when they hit the target here. So what is that flavor change?
Yeah, that's right. So the accelerator in Fermilab will produce this really intense beam of neutrinos, shoot it through the Earth, no pipe. The neutrinos travel right through the rock, hardly even know it's there. Interact with large vats of liquid argon 13 million gallons of liquid argon will form the target for the DUNE experiment, the Deep Underground Neutrino experiment. And there they will look for these differences. So they'll shoot a beam of matter particles, neutrinos, measure the properties, count the number of interactions, then they'll change that to an antimatter beam, an anti-neutrino beam, shoot that beam through the Earth, just like they did with the neutrino beam, and count the interactions and look for that difference. And that will help them understand whether the neutrino has this slight preference for matter over antimatter. We believe that's the case. We believe that the neutrino has that hidden in its properties. But we're trying to really narrow that down with this multi-billion mega science project, the DUNE experiment, the Deep Underground Neutrino experiment at the Long Baseline Neutrino Facility here.
And at the end, if you can detect that even a 1 in a billion has a slight preference for becoming matter rather than the anti-neutrino, then that would kind of clear up why most of what, or be one signal in helping to clear up why most of what is observed out there, stars, planets, etc., are matter and not antimatter.
That's right. It's a really fundamental puzzle that we look in the universe, tables, chairs, stars, planets, galaxies, they're all made of matter. In the early universe, after the Big Bang, we know that equal parts matter and antimatter were formed. We don't see any of that antimatter except in the accelerator centers where we can produce small parts or small amounts. So this would be a massive signature for something that is really fundamental to our existence and finding it out in the smallest of particles.
So let's talk a little bit about the dark matter experiments that you're doing too, right? So a lot of current scientific theory would suggest that a large portion of the mass of the universe should be dark matter, which no one has ever observed. And you've run a bunch of experiments here that have been some of the most advanced in the world that have still not actually picked up or observed dark matter. But I'm curious to hear what you're working on next and why that's important as well.
Absolutely. So 5 times more matter in dark matter than compared to normal matter. So it's also a very fundamental, very significant part of our universe. We just wrapped up running with the Large Underground Xenon experiment that uses xenon as a target. And that ran and was the world's leading experiment in terms of sensitivity for almost 4 years. That experiment has been decommissioned, it's run its course. We're ramping up now to start construction on the LUX-7 or LZ experiment. That will have 30 times the volume or 100 times the sensitivity, looking for the signature of dark matter, as you said, no one has ever seen before. We have indirect evidence. We know that the rotation speeds of galaxies are too fast. The matter that we see, the galaxies should fling themselves apart. We also see evidence through gravitational lensing, space-time bends, with some mass that we can't see.
It's interesting because all of the projects, yet they're different, but they all overlap in some matter. The large neutrino experiment looking at neutrino flavor, dark matter, even Myrana, we all are looking at this very low energy region of interest where these things can occur. Yet they're separate, but they're the same.
Awesome. All right, well, thank you for taking the time to explain this, both explaining it to me earlier in a little bit more detail and for explaining it to all the folks who are watching now on live. I want to make sure we get a moment to talk about the community implication aspect of converting this from a gold mine to a big science research facility. So Dan here has some really interesting perspective on it because you actually worked here when it was a gold mine.
Correct.
And have had a career here now working through it being a big, massive underground science lab. So I'm curious to take us through what you've seen and what the facility, how it's evolved, and also not just here, but the community around here and how that's been shaped by changing from a natural resource-based enterprise to one that's more about science and knowledge.
Well, I started for the Home State Mine in '72. There was about 2,200 employees, and through the transitions of the cost of gold and the production methods and stuff, it transitioned over the years till about 1998, when Home State Mining Company was taken over by Barrick Mining Company, and the decision was made to cut down about 50%. They realized after a few years that wasn't going to last, so the mine was closed and went into a closure property. At the time that they decided to close, 50% of the workforce was laid off, and they transitioned over the next few years. So in that period of time, those people that had been laid off transitioned into jobs. Fortunately, the Wyoming coal fields were close by. A lot of guys went that way, a lot of people. Others reinvented themselves, and that's what I did. I started my own business and came up with a business that found a way to make a living around here. I was fortunate to stay in the community, but the community was reducing in size, and I was on the school board right when it closed. There was about 1,100 students in our school district, and within a few years now, we're down to about 800, I believe, is the last count. But the size of the community has changed tremendously, and it's about 2003 the transition to the possibility of the science came along, and groups were starting to work towards that. And then with Pete and Sanford's support, the mine was able to, or the underground research was able to restart, and so groups were put together to reactivate the equipment. I was hired on to help restart that, and then within a few years there was enough equipment where the reentry started to repump or pump the water out and get it out so the science could restart. The transition as far as the rest of the community is other people reinvented themselves, found new professions, some moved away, stayed in the mining business.
All right. Well, I mean, this facility is super interesting. I mean, in order to get down here, I know we were talking for about 11 minutes during the elevator ride down here, which is this, I guess you guys do this every day, right?
It's a cage.
Sure. Well, elevator might have been a euphemism, or maybe a little more nicer than it actually is. But I mean, that's basically the function that it serves. You walk into it, it's a lift, right? And it takes you down a mile, and it takes 10 or 11 minutes, and it feels like something that would have been in a mine, right? Not in an office building or something like that. So, but in a lot of the facility here, you've had to basically rework and make sure that it can work for the kind of science that you're doing today.
We're in the process of improving all those infrastructures as we speak. We're not done yet. We made significant improvements, added new technologies to it, and there's future improvements to that technology to make it more efficient, more dependable on the use of it. So, like you said, when I first started, it'd take 3 minutes to get down here. Now, quite a bit longer, but that was designed that way to be a safer transport while the rest of the infrastructure is improved. But it was quite a deal for a 19-year-old like myself that had never experienced industry to come here and be exposed to it.
Yeah, I can imagine. All right, is there anything else that you guys think we should cover while we're here?
Nope.
All right, well, thank you so much. I mean, I think the science work that you're all doing is going to be really important. So I'm grateful for it. I hope more people who are watching this think of going into science research. I think this is really long-term and important work for the world, which is why we try to support it through the Zuckerberg initiative. And I am just really optimistic about all the work here. And just as a community and how it's evolved, I think it's super interesting as a case as I've traveled around the country of communities that have evolved from doing one thing historically to doing another and modernizing. So what you're all doing is really impressive. So thank you for taking the time to show me today. Thanks. All right.